Hi everyone, my name is Dmitry Ukrainsky and I'm going to present you our team's solution, the third place solution in the CIBMTR Kaggle competition. So for agenda, it's quite standard. Some information on background of our team. For me, I have a master's degree and a PhD degree in mathematics, more precisely in continuum mechanics from Lomonosov Moscow State University. I'm working as a quantitative researcher and chief data scientist in the financial industry, and I'm a Kaggle competitions master. My teammates, Nikita Churkin is a data science team leader in e-commerce industry. He has 2 master's degrees, one in mathematics from Lomonosov Moscow State University and one in computer science from the Higher School of Economics. He is Kaggle competitions grandmaster. Sofia Ukrainskaya, senior data scientist in the financial industry. She has a master's degree in finance from Lomonosov Moscow State University. And Evgeny Hinenzon, a data science team leader in real estate company. He has a master's degree in mathematics from Lomonosov Moscow State University, and he is a Kaggle competitions master. So all of us connected with our university. Short summary of our solution: private leaderboard score, training time, model zoo. All of these details will be disclosed more comprehensively in the next slide. So let's move on. Modeling approach. We divided the task into 3 different parts. Separate regressions within uncensored and censored time, weighted on the probability of belonging to each of these 2 classes. For the target variable, we made a uniform target in the range 0.1 for uncensored observations and in the range 1.35 plus minus 0.05 for censored cases. For censored cases, their regression, so the regression for censored cases is the most insignificant part of the solution. And for example, for neural networks, we just collapse all the range into a constant 1.35 and use this constant instead of the whole regression. The range for censored cases were optimized in terms of concordance index on our validation. So this range was taken as optimum one. The target variable was calculated within trained faults and valid faults separately to avoid any leakage. It also was calculated separately for every race group, because the key metrics of the competition was the concordance index calculated independently for every race. It also should be mentioned that the target range 0.1 for the regression task allowed us to train the models via binary cross-entropy loss, which is much more profitable according to our experiments in comparison with mean squared error. So here you can see the resulting ensemble. We also tried ranking models, but they have weaker performance in the competition. We believe it is a consequence of not so large training data set. So for classifier, we use the staking by logistic regression. So sigma here is the sigmoid function. For uncensored regression, we used the convex combination. And for censored regression, all of the weights for boostings are equal, and only the shift parameter was tuned to maximize the concordance index. As I had already said, for neural networks as the solo models, we just replace the censored regression with a constant 1.35, just collapse the target range into a constant. All the blading weights were optimized simultaneously to maximize concordance index on 20 out-of-fold predictions by Bayesian optimization. You can see also here the visualization of our ensemble. Regarding feature selection and engineering stage, we tried a lot of things, but almost nothing worked. The only one method that improved our score was just to calculate the counters, simple frequency encoder. We also tried merge the categories, make multi-category combinations, encoding missing values, the whole variable by other variables, make features based on the number of missing values in a row to catch some rare data pattern or outlier data pattern, make text features, group by features, anomaly detection features like isolation forest. We tried target encoding, including double cross-validation to avoid leakage. We tried decomposition features, SVD, PCA, factor analysis, tried to make Kainan features using decomposition features, tried autoencoders, denoising one, variational one, related to presentation of input, but nothing worked. We believe that feature engineering is not worked because of data being synthetically generated, and for this reason also any feature eliminations or poor performance. We also tried to generate additional data, tried several generative adversarial networks, but they also didn't lead to a substantial scoring increase. Anyway, regarding feature importance, here you can see two plots for light GBM. The first one is for uncensored regression, EFS equals 1, and the next one is for classifier, EFS flag classifier. So as you can see, some counters are in the top of the list, but the majority of features in the top list by importance are just original ones. Regarding important and interesting findings, I want to make special attention to the validation. According to our opinion, it is one of the most critical aspects of this competition. If you will try to use only one random split seeds, you will see the same variation of score when changing this seed. And it is enough to evaluate incorrectly almost any, at least non-major improvement. So for us, we made a fold cross-validation. Fourfold because the public part of the test were 25% of its entirety. And we evaluated the score by 20 plus random split seeds. And during all the competition, we had excellent CV versus LB correlation when measuring average false scores, 4 folds multiplied by the number of seeds. And the public fold was approximately at 75 quantile of our histogram. So here we can see the score histogram for one of our experiments. The public fold was approximately here. And this approach allowed us to climb the leaderboard really stably. It is also interesting that survival analysis is a fruitful branch of mathematics, but classic models, modern open source neural networks for survival analysis, other approaches didn't show competitive performance. Nevertheless, some papers, for example, we highlight here the paper from the author of Deep Kernel Survival Analysis. This paper helped us really to dive deep into the subject, and it was really great pleasure for us to learn the new branch of statistics and probability. It was a really classic one. It was also very important to work with outlier denoising. For example, we average the models with fixed hyperparameters and architectures over their random initialization seeds. So for boosting models, it's model initialization seeds. For neural networks, it's both model initialization seed and data loader initialization seed. In the forum, it was called model repeats. So it helped us a lot. And we also eliminated the observations with the highest binary cross entropy. It's outliers like the one presented in the green circle on this scatter plot. We eliminate them from the trained faults, not valid faults, only trained faults for uncensored regression. They are unpredictable. In this setting, you can do nothing with them and mess the training process. So we try to eliminate them, and it helped helped us to improve our concordance score. We also tried this in the case of classification, but this outlier denosing leads to overfitting. For example, ROCAU becomes better, but log loss and concordance index also worsens at the same time. So for classification, we rejected this hypothesis. Regarding solo model performance, here we can see the table. Each of row in this table is the architecture that was used for all of 3 tasks: uncensored regression, censored regression, and classification. So cut boost, light GBM, XGBoost, neural network, the blending of boostings, and our final private leaderboard score. For neural network model, as I had already said, we replace the censored regression with a constant 1.35. Here you can see the scatter plot for this model. So you can see how this picture looks like in this replacement. Neural network is our best solo model. It is MLP classifier with ODST layer, oblivious differentiable sparse trees from PyTorch tabular in composition with the TABM regressor. TABM is a new model from Yandex Research, quite nice. So this model shows, this composition model shows gold zone performance for 20 minutes training from scratch on Kaggle and 4 minutes for hidden test inference. We published this script as a public kernel and share the link here. As for final slide, solution overview, I want to make special attention one more time to the most important trick in this competition. It was to divide the task into separate regression and classification parts according to write-ups, according to today's presentation. All the winners used it. But how we can see this trick? For example, we can see it looking at a scatter plot within the first modeling attempts in the competition. So in the very first steps, we tried to make an overall simple, naive regression on logarithm of AFS time. And scatter plot looked as following. We have quite bad regression here with 2 blobs. The model systematically overestimates uncensored observations and underestimates censored ones. So these blobs will help us to come up with an idea. What if we will try to make separate regressions, each own in its segment? So the regression using only EFS equals 1 data and regression using EFS equals 0 data only. So in this case, centered and right-sided pictures. So in this case, if we will use only uncensored data, the regression for uncensored observations will quite nice. It's quite good regression. But of course, the censored observations are not predictable at all. And the analogous situation when you are using for training only EFX equals 0 observations. So it pushes us to make separate regressions for each of these 2 segments and make a special classifier that will aggregate these regressions into a final prediction and distinct between these 2 classes. So on this stage, it will necessary to decide which classifier should be used, the classifier weighter or classifier switcher or someone else. So classifier weighter just weighting the regressors by the probability of belonging to each of these classes. Classifier switcher just choosing one of the regressors for every observation based on the probability threshold. And for most cases, including for this competition, the classifier weighter works much better, and we decided to use it. So we also share here the full code of our solution, the link to our write-up. That's all for us. Please